This is all here, yes. Okay, so I've decided to spend a little bit more time on Faraday's law. We can't do all of induction in one lecture, I think. So we're going to do a few more example problems and see some consequences of Faraday's law. All laws have consequences. And then I decided next week we'll start modern physics. I'll go ahead and pick up NMR and MRI today. So today you'll have some idea how those work. You just need to understand them at a basic level, kind of like mass spec. Right? We'll write homeworks about them, but it's really just the physics that we're doing. You don't need to memorize any quantum chemistry or anything like that. Okay, so Faraday's law of induction, we talked about a few ways. You know, the basic idea is that if the magnetic flux through a loop changes, you generate an EMF in the loop. If the magnetic flux through a loop changes, you generate a little EMF, an electromotive force, a little voltage around the loop, whatever that means. You'll generate some current around the loop. Okay? So now we're going to do a different problem, though, because how did we do it? We had a loop in a field, and we dragged the loop out of the field. And that caused a change in the flux and an EMF. We dropped the loop far from a wire, and as the loop went away from the wire, the field went down. So there's different ways to change the flux. So here we're going to look at arguably the most important way to change the flux. So we have a loop. So this will be kind of like a problem you could do. A loop, we're going to do it with numbers, of radius 8 centimeters and resistance 20 ohms. Because remember, EMFs are voltages, so often we'll give you a resistor in the loop so that you can convert it to a current. And it's going to rotate at 3 revolutions per second. All right. That's new. We have something rotating, okay, in a uniform B field of half a Tesla, 0.5 Tesla. There's a problem, and the question is, what is the maximum current? And that does not disallow 0. Maybe it's 0. Maybe this will make no current. So let's start by drawing it and figuring out what am I talking about here. So let's say the magnetic field points into the loop, or points into the board here. I'm going to get my words right today. Working on my words. And so the field into the board. So here's your 0.5 Tesla into the board, and the loop is a big circle. Say here, like now let's center it here. Artistry, so important. There is the loop, like that. And if it's rotating, it has to rotate about an axis. So let's go with this axis right here. This is what I meant. So the problem would have a drawing like this, just to let you know. You need to know the geometry of the rotation relative to the field to figure out what's going on, right? Because that tells you how the current is moving relative to the field. And we're going to say it's rotating. If you're into vectors, you would say the omega vector is like that. That means it's rotating around that axis. If you're not into vectors, you would draw 2 little things like this. You'd say, okay, that side is going in, and this side is coming out. You could think of it that way. Or if you're really not into technical things, you could draw a little arrow like that. That means it's going around. If you're really into the right-hand rule, and all I gave you was that omega vector, you could still figure out which way it's turning. Because you'd say, oh, that's the right-hand rule. That's where anything straight and anything turning go together with my right hand. So the omega vector is straight. Yes. So which way is it turning? Oh, it must be turning like this. Right? So by definition, if omega is this way, it's turning that way. Okay? So there's 3 ways to tell you which way it's turning. This side is going into the board. This side's coming out of the board. Okay. Now, is there going to be a flux, a change in flux? Okay. First, is there a flux here? That's the first thing we could ask ourselves. Is there a flux at this moment? Yes, because there's an area here and there's a field going through. If this were if the loop were the hula hoop and the fields were the wind, then of course I'm blowing through the hula hoop. There is a flux. Good. Is there an EMF? let's see, at this moment, because it is moving. So we just have to ask ourselves, with this kind of motion, would we expect the charge to move in a way that would build up an EMF? So let's just look. Let's think the current, the charge carriers here. So you have a little positive charge carrier here. We would say, let's see, V of that charge carrier is into the board, and B is into the board. So no, there's no force, no FB here. What if we come a little charge carrier over here? V is QV cross B. So here V is out of the board, and B is into the board. And again, it's 0 because they're here, V and B are parallel. Here, V and B are kind of like anti-parallel. They're 180 degrees from each other. So I guess one thing I don't know if I explicitly said this, you could probably tell from the formula, if you have two vectors A and B, and you want to take the cross product, A cross B, right? Fingers along A, curl them to B, cross product is in. If you have two parallel vectors, A and B, their cross product is 0, right? Because you put your fingers along A, and there's no special way you have to rotate them, because they're also already along B. That means the cross product is 0, right? So A cross B equals 0. A cross B. But it's also true that if you have A this way and B this way, 180 degrees apart, that cross product is also 0. Right? You don't know which way would you curve them. It doesn't matter. They're the same direction. It's A, B, sine theta, sine of 180 is 0. So here, A cross B here is also 0. Just FYI. Whether they're parallel or anti-parallel, it's 0. So what we find is, well, what if I put it here? Oh, this guy isn't even moving, right? That's where the radius of the circular motion is essentially 0. So that charge, that doesn't. What if I go here? I'm sorry, a little charge carrier here. These are charges, by the way. This one is moving into the board. It's sort of a three-dimensional motion you have to think about. If I look down on it, this one's moving in. So again, even this one, no charge carrier feels a magnetic force. So FB is 0 everywhere you go. So if there's no magnetic force pushing charge carriers around, there's probably not going to be an EMF. We'll prove it with Faraday's law in a minute, but just our initial intuition says nothing is moving here. All right? Nothing should happen. Let's go ahead and be bold and say the EMF is 0, just based on thinking about forces. So you say, oh, it must be 0. Yeah, we're not done. Obviously, the geometry is all going to change as that thing rotates. So what we got to do is draw it in another orientation. Okay? I'm going to draw it by the GoPro convention. Okay? The GoPro convention means I'm attaching one of those ridiculous helmets to the loop. Okay? We're looking at the loop's view. The loop is going to turn this way, and we're still looking at the loop. Okay, so we turned with the loop. Okay, so here's the loop again, and this is 90 degrees later. Well, if we turned with the loop that way, which way is the field? There it is. I'm going to come around here. Oh, the field is this way. The field's to the right. So 90 degrees later, it looks like this. The field is going to the right. All right. If I came around here, GoPro style, to the right, the axis is still here. Right? Omega is still there. It's still going around like that. This is still going in, and this is still coming out. So the loop is the same, because we're attached to the loop. But the field changes. Okay? That's all we're saying. So this is just the next view, 90 degrees later. All right, so now let's ask ourselves, is anything feeling a force? Let's see, here is a positive charge carrier. V in cross B out. Oh, it feels a force down. FB. So there's a chance that we will have a little EMF here. Or will it just get polarized? Let's find out. Let's say, what's going to happen to a little charge carrier here? I'm excited. I don't know what's going to happen. I forgot. V cross B up. This one feels a force up. All right. Why not? Let's do a charge carrier here. I didn't plan it in my notes. I'm sure something will go wrong. That's what makes the class exciting. What's the force there? Somebody shout it out. What's the force there? 0, right. When I do that, that means the answer is 0. Whoa. 0. Why is it 0? Why did you say 0? Did you know physically why, or because I went, what's the force there? Why is it 0? Because V is 0. It's not moving. Right? Remember, this thing is rotating around. For Faraday's law, you got to think about the motion. So the thing on the axis isn't moving. So there you go. If we went here, you'd say, okay, that's also moving in, blah, blah, blah. It would also feel a force down. So basically, you would expect to get circulating charge here. So if you like to just use your forces on charges, you can do that when something is moving usually. And you would conclude that FB, I'm just going to say it's not 0. Right? It changes direction as you go around the loop. It's going to create a circulating kind of a force. Therefore, the EMF is not 0. Right? Interesting. Let's go 90 degrees later. 90 degrees later. We're attached to the ring, GoPro style, and now the field is the other way. We aren't going to do this one as detailed. It's going to go the other way, but we're attached, so the velocity still looks like that. And the forces in the EMF here is 0 again. Right? Because we have our velocities in the same direction or anti-parallel to the field. Right? So FB equals 0 again. FB's equals 0, and the EMF, we could say, is probably 0. Okay, so what have we done? We have a situation where, because this thing is rotating, it appears that we have no EMF, and we have an EMF, and we have no EMF. And if I flipped it 90 more, we'd have an EMF again. So we have an oscillating EMF. That's our conclusion just by kind of just not doing the math yet, just by thinking about sort of the F equals ILB force, or the QVB force. So the conclusion is an oscillating EMF. That's the sort of just hand-wavy conclusion. Okay? So now what we want to do is see if we would conclude the same thing mathematically. Let's see. Would we also conclude an oscillating EMF? Although before we do the math, we could think about it again. So we thought about it in terms of ILB forces or QVB forces, whatever you want to call them. We could also think in terms of fluxes. Is the flux changing here? Is the flux oscillating? And the answer is yes, right? In this geometry, if the B field is the wind, then there's a lot of flux. There's a lot of wind going through the hoop. What about in this geometry? No, right? There's no flux here. The field is not going through the hoop. It's going past to the side of the hoop. And then it rotates again, lots of flux. Right? Now you may say, why is it when there's no flux there's an EMF? Well, that's because it's the rate of change of the flux. It's not actually equal to the flux. But the point is you can tell that this is a case without moving the loop and without translating the loop, and in a uniform field you can still get a changing flux because you can rotate something. Right? It depends on the dot product between the A and the B. Okay, so now that has totally gelled in your mind, now let's do it mathematically. Let's use Faraday's law to calculate it. All right, what was Faraday's law again? E equals minus number of loops. The time rate of change of the flux is what we care about. Hey, this is a calculus-based course. Look at that. All right. What is phi B? Phi B is, now somebody texted me last night, I think they were bored, really wanted to know, couldn't wait, and said, it's okay, I don't mind. I don't think I answered it though. And said, will we ever have to do a case where the B field is not uniform? And the answer is no. Because that would be vector calculus. And we're just doing sort of mental vector calculus here. We're just doing constant vectors where you think, okay, I got to take the field direction and the area direction and kind of dot product them. We're not doing the case where the area is curved and the field is non-uniform and I got to write some horrible integral. Right? We're just doing kind of the basic idea. So yeah, your B fields will always be constant if you have to do something numerically or quantitatively. Right? When we dropped the loop, in the last lecture, we just did Lenz's law to get a direction. There, the field wasn't uniform. But we didn't ask you to calculate the flux either. We just said get a direction. So you might have a non-uniform varying field, kind of a Lenz's law, which way does the current flow problem, but not like here where we need a number. Okay, that's the answer to the text. There you go. That's how exciting my DMs are. Do we need to know the flux of the let's see. So phi B is what? Phi B is the magnetic field magnitude times the area magnitude times the cosine of the angle between them. BA cosine theta. Right, that's the flux. All right. Now, let's draw this and look down. Okay, so now we don't have the GoPro view. Now we're actually looking down on the thing, and I'll draw the field to the right just to make my life easier here. because it's all about me here, guys. Let's see. Right, so there's your A vector. We're looking down on it, so it's going around kind of like this. Right, and your A vector is rotating. So how do you describe a rotating vector like that? When something rotates, how do we get omega in here? This is the trick. Is you write a function for theta as a function of time. And if we go back to last semester, prereq, rotational motion, theta is a function of time for constant rotation, omega t. Right? Theta is omega t. That's just like d equals vt. Theta is omega t. Okay. So all we got to do is stick that in there. And then we have how the flux is going to change with time. Okay. So let's do that. Let's see. Now first let's write theta. Okay. So now let's solve the problem. So now we're going to start plugging in numbers because I can feel it. We're within striking distance. You know when you're doing a problem and you know you're within striking distance and you're all proud of yourself and you put in the answer and then you get the red X. And it's so depressing. I know. Okay, so let's write a function for theta. Let's start plugging in the problem numbers now that we're in striking distance. What is omega? Prereq. 2 pi f, right? So if it's going around 3 revolutions per second, each revolution is 2 pi radians. So if we wanted it in omega, it's got to be 2 pi times 3 revolutions per second, right? Times t. So theta function really is just 6 pi t. So if I were doing it numerically, I like to break it into little pieces like this. I don't put it into maple on my calculator or whatever you guys do. Okay. Phi b then. Okay, so now we have a function, so we can put that function into phi b because I feel a derivative coming on. I can sense when functions and procedures are coming. So phi b is b half a Tesla a. Which a is it? Well, there's only one area. It's pi r squared of the loop. We'll get into confusing areas later. Pi 0.08 meters squared, right? B, A, cosine 6 pi t. Yes. Well, what we're trying to do, we're not trying to calculate the flux, we're trying to calculate the EMF. We could take a second and realize, oh yeah, the flux varies with time, and it's a cosine. So yeah, it probably does hit 0, and then a value, and then 0, then a value. Just to make us feel better. Okay, so the EMF is then what? The EMF is, let's just copy it down, negative. The quality of the erasing is just too damn low. Negative 1. Because our problems all seem to always be one loop. On the exam, I'm sure we'll add more loops and just be a jerk. Okay, so minus 1. And now the derivative of this with respect to time. Oh my God, look at all that. Well, this is all just a constant. I think I combine the constants. Yeah, when you combine all of this, you get basically 0.01. Negative 1 times 0.01 in whatever unit that would be in. Tesla meter squared. Okay, so this is all of these. Now we've got to take the time derivative, or the derivative of cosine 6 pi t. This is the calculus-based part. I know you can do it. The derivative of cosine's negative sign, and you bring out the derivative of the thing in the parentheses with respect to the independent variable t. All right, so we say, what's the derivative of this? 6 pi. 6 pi. Derivative of cosine is negative sign. I'll put the negative right there, if you can handle that. Sine 6 pi t. Boom. All right. So it looks like the two negatives cancel. It looks like, I need a spillover board. That's what I'm calling this now. I have no eraser. It looks like the two negatives cancel. It looks like the 0.01 becomes 0.06 pi. So we can write a final function for the EMF. The EMF you're going to get is 0.06 pi sine 6 pi t. And then you get to that point of the problem where it's like, I forgot what I'm calculating. That happens to me a lot. All right, I'm just writing and getting excited and then realize, what? What was the question again? What was the question? What is the max current? Yeah. So here we have the oscillation of the EMF with time. And I guess we didn't really technically do AC circuits, but if you just have voltages and resistors, then when they oscillate, if the voltage you apply oscillates, the current oscillates. And the resistance is constant. So that's all it is. So if we want the maximum current, we need the maximum EMF. So based on your knowledge of mathematics and calculus, pre-calculus, no, calculus is required. The maximum value of this function is 0.06 pi. Right? Sine goes from 1 to 1, so E max is 0.06 pi. It would be in volts. If I was keeping all the units as I went along, it would end up in volts. Oh my God, my phone is off. So many questions. Let's take a break and answer some questions. Let's see. Why did the velocity change from both being the same way to opposite after 90 degrees? Oh, that's probably just a typo. Now, the velocities are opposite there. That's velocity and that's velocity. And they're opposite there and they're opposite there. Sit closer. No, I'm just kidding. You don't have the option to sit closer, I know. I'm sorry. Can you explain how you got the picture again? Oh, I would have to have caught that at the right time. I don't want to re-explain all the pictures. Did you not use the resistance 20 ohms value? We're not finished yet. We're getting there. We've got to take our time. You guys are always in such a rush. We got 75 minutes here. This happened when I took the derivative. DDT, it's a calculus-based course. Yes. DDT, I took the time derivative of that flux, and that's when cosine became sine. The derivative of cosine is negative sine. Yes, that's correct, yes. Okay, I haven't used the resistance yet because we're not done yet. Okay, so now we want to know how do we get from the voltage, the EMF, to the resistance. It's just like Ohm's law. You treat it like Ohm's law. You say the maximum voltage difference you apply, an EMF is not exactly a voltage difference, but it still works, equals the maximum current times the resistance. Right? So for the real answer, then, the final numerical answer for this, it would be that the I max equals the 0.06 pi over the 20 ohms. And I got like 9.4 milliamps. Yeah, so then we're done. Right. Mm-hmm. So we're thinking of it just as a little circuit, although it should weird you out a little bit. The fact that where's the voltage difference? Why? I mean, how can you just apply V equals IR and say there's a voltage difference around the wire? Because where is it? Like, are we at high voltage here and we go around and we've dropped by an EMF of E, but how are these two touching and be at a difference of the EMF E? How does that work? Yeah, that's because field theory is weird. That's how it works. Okay. So all the rules you use really were for electrostatics. The way we treated circuits and Kirchhoff's laws are really sort of just an approximation for static fields. Even though there's current moving, it's basically a static field. Right? The fields aren't changing, it's just the current is moving. If you allow things like this to happen, and you get alternating magnetic fluxes, and you get electric fields that are changing in time, they don't follow the rules of electrostatics. And it's not true that when you go around a loop, you have to end up with the same voltage. Right? That's only true for static, conservative fields. This is crazy field. It gives you a headache. Don't think about it. Okay, don't worry about it. We're not going to do non-conservative electric fields. Too confusing. Faraday's law. Are we feeling better about Faraday's law? Yes. I'm going to take your silence as acquiescence. Let's see. I think that was the wrong word. Okay. We're going to do another one because I love you so much. We're going to do another practice Faraday's. Oh, wait, I'm sorry. That's the generator problem. Yes. Okay, so this is the basis of how generators work, right? The dam turns the turbine. It spins a loop in a magnetic field, and it makes electricity, right? Or the nuclear reactor heats up some water and makes some steam. The steam pushes a turbine, and it makes electricity. Right? The wind turns the turbine, makes electricity. So this is the basis for generators, all thanks to Faraday. So no matter what kind of energy generation you're using, you're eventually doing this to make electricity, because electricity tends to be how we, spread energy around, except for gasoline, but we'll be out of that soon. Okay, but I want one of you to experience this, so I need someone to come help me with this, someone who's very, overly expressive, someone who really, a lot of drama, they don't really keep it in well, Like if something changes, they're going to go, oh! I need somebody kind of like that. Does anybody want to admit they're like that? Okay, if you're not like that, I'll be like that, and I just need you to turn a switch. How about that? Okay, somebody come turn this switch. Anyone, this is it. I mean, once you go into the real world and life is boring, I had these seniors come back, they're like, well, yeah, I'd really like to do something more intellectual. They would have wished they should have come down. This memory of physics, here's what you have to do. I'll do the drama. You have to do this. Someone come do this. No one brave enough. There, get down here. All right. What's your name? Kevin. What college are you from, Kevin? Brown. Nice. I've run out of shtick. I don't have anything for Brown. Okay. So come over here, and I'm turning this, and I'm turning a loop in a magnetic field. And I'm not getting any power generation, right? And it's because the loop is not finished. The loop is not complete. So when he throws that switch, suddenly it's going to close the circuit, and I'm going to have a loop in a magnetic field, and we're going to see what's going to happen. Okay, turn that little switch. Oh, God! It's so much harder to turn! Help me, Kevin, help me! Okay, no, so you see what's happening. Oh, thank you. Ah, thank you. Thank you, Kevin. And I broke it. All right, cool. So let's think about what was happening here. I was showing you this really is how you generate electricity. So somebody, God knows how long ago, back when people used these, built a little thing. Oh, I really did break it. I'll fix it later. Wow, I got too excited. There we go. When you turn the little thing, it's turning and it's making current, and current shows up in the light bulb. But if you want to go a little bit deeper than that physically, the reason it gets harder to turn is I'm having to do work to do this. Right? I mean, you don't get energy for free. So when the circuit is open, no current flows. I don't have to do any work to push the current through the bulb. But as soon as he flips that switch, I'm literally doing the work to push the current through the bulb filament. It's like I physically have to, I'm just shoving it through so that it can heat the filament up and make light and blah, 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 blah. So we will do a numerical example in a minute where we calculate, or we convince ourselves that you really have to, it takes a force to do these things. They don't just sort of happen magically here. We could calculate it. We didn't do it as part of the problem, but we could also calculate how much power is being put in, right? P equals IV. So if we have a current I and we had the EMF E, it would just be I times EMF. So we were doing work and power there. And that's really the main application of this, is generators. So that's why I wanted you to see there's power involved. Now let's do a problem with a solenoid. Did I waste a whole half of a class on that? Almost. Okay. A solenoid in a loop. Not waste. I mean, I didn't mean to say waste. In a loop. A solenoid in a loop. Okay, this is another one that illustrates a critical point. What is the loop current if IS is KT? Oh, God, that's one of those where we're being so cruel. But it would also come with a picture that might clarify things. So let's start with the solenoid. IS, so the solenoid has some current S going through it. This is one of these things where it's got, some number of turns per unit length, right? Because it's a solenoid. I guess I'll put NS. I mean, it's the only solenoid in the problem, right? That's fine. And we're going to say it has some radius, RS, like that, okay? A solenoid, and it's in a loop, so we would draw this for you so you see what we mean. Now there's a big loop out here, and I'll remind you that it has a resistance like that. All right, so you can see the solenoid's going through the loop. It's supposed to be perpendicular, but I'm trying to draw here. The question is, what kind of a current are we going to get in the loop if it has some resistor there, and it also has its own radius? Okay, big R is the resistance, and it also has RL. So the point is, there are two different sizes, right? A small solenoid, little RS, a big loop, big RL, with a resistance R. Now, first of all, would we expect there to be any Faraday's law EMF at all? The answer is yes, because we know this is going to create a magnetic field, and if we have the current varying in time, you're going to have a varying magnetic field inside the solenoid, right? Basically, we're ramping it up. So let's go ahead and draw that part. Let's plot what's happening in the solenoid. Here's the current in the solenoid as a function of time. Can we plot KT? Yes, we can. There we go. Starts out at 0 and increases linearly with time. What if I said, plot me the magnetic field as a function of time in the solenoid? Bs, B in the solenoid, as a function of time? Well, you go back to your formula and say, what was it? It's mu naught little n I. Mu naught is a constant of the universe. Little n is the number of coils per unit length. That's not changing. So B is just proportional to I. It's just like this. It's also a line. So if we look at that, you can, at the beginning, say, okay, yeah, for sure, there's going to be an EMF induced because I have a changing magnetic field inside this loop. So there is going to be an EMF. Let's calculate it. This one we're doing symbolically. What is the EMF in the loop? It's minus number of turns of the loop, d phi b of the loop over dt. The point of this problem is to separate in your mind which areas matter when. Right? So when you write this, you basically put the same subscript here, here, and here. It's not like Coulomb's law of forces where you say 1 on 2 and 2 on 1. You just say no. The EMF induced in this loop depends on the flux in this loop and the number of turns on this loop. Okay? Okay, so let's go through and see what those are. Equals, minus, again, 1. We keep not only putting one loop. If it went around twice, it would be 2. We're just doing 1. ddt, the time derivative of BA cosine theta. There we go. All right. So now we say equals minus d dt, the time derivative. Just got rid of the 1. And now let's plug in formulas for all the things in the parentheses. All right. Let's see. And one of them had better depend on time, or the answer is 0. So I hope something depends on time. The B field. What is the B field? Oh, that's the one that depends on time. All right. So if we want to be clever and do it in one step, we would say mu naught in I is the B field inside a solenoid, if you remember from a week ago. Mu naught in, but now I'm going to be wild, and I'm going to go ahead and write the formula for I, KT. Because which I is it? Is it the I of the loop or the I of the solenoid? The B field inside the loop is the B field created by the solenoid. And the B field created by the solenoid depends on the current in the solenoid. All right? So even though I wrote that we're doing the flux in the loop, the flux in the loop might depend on parameters from the solenoid. Okay? I'm going to put that here because that's the key to a lot of these problems. The flux in the loop depends on parameters of the solenoid. So I made a big deal about putting L here, here, and here, but that doesn't mean the answer is always going to be L. Okay? This might depend on other things. And the perfect example is here, right? So B is mu naught Ni for the solenoid, and I for the solenoid is KT. All right, so I'm going to put a little reminder there. That's I for the solenoid. Okay? So mu naught NKT. And and then what is A? This is a hard one. Think for yourself for a minute. What do you think? Which A is it? Which A? Is it area of the loop or the area of the solenoid? Partial credit, it starts with pi. Yes, it starts with pi. Something is squared. Right, probably a radius. But which radius? It's the radius of the solenoid. Right? It's the radius of the solenoid. Hopefully you guessed, or hopefully you figured out solenoid. I mean to say guessed. Why is it the radius of the solenoid? Because it's the magnetic flux. It's B times A. So if we think about this loop, what's really going on? It's the flux in the big loop. Okay? So here's the big loop. But where is the magnetic field in this big loop? It's not everywhere. It's not a uniform magnetic field. It's just right here. Right? Or maybe it's the other way, whichever one it is. Right? So the flux itself is really just that magnetic field times that radius, or that area. So that's why this problem is tricky. This one depends on the size of the solenoid, not of the big loop. Right? So RS right there. And then the cosine, and nothing is rotating here, and we'll pretend my diagram is, pretend they're perpendicular, we'll call it 0 degrees. I mean, I drew it kind of funny, but you get it. This was supposed to be that way. All right, so that's just 1. Yeah, So that is the EMF right there. We can simplify it probably a teeny bit here. So if we want to get our final answer here. But simplify this thing. Oh, we haven't taken a derivative yet. Yes, of course, we still have to take a derivative. So the EMF is minus the derivative constant mu naught, constant n, constant k. The t is what we lose in the derivative, t to the 1. Drop the 1 to 0, t to the 0 is 1. All right, there's your derivative. Pi rs squared, cosine of the 0 is 1. Right, so there's your EMF. All right, mu minus mu naught n k pi I. Now, what was the question? What were we asked again? I forgot. What is the loop current? Oh, we were asked the loop current. Right? So just like before, we got to use the resistor to get the current. So I didn't mean to make these two problems exactly the same. Should have asked for the power or something. So we just take that minus mu naught n k pi rs squared over big R. And there's your current. And you'd say, wait, it's constant. So in this problem, the current changed in time. Why is it constant here? And the answer is because the time rate of change of the field and the flux and the current is constant. Right? This is just a linear function. So we took the derivative, we got a constant. Over here, we took a derivative of a time-varying sinusoid. We got another time-varying sinusoid. But here, derivative is just constant. There it is. There's the current. And it does depend on the size of the solenoid, not the size of the loop. What else do I want to say about this? What about the direction? Can we get the direction? Not really. My drawing isn't good enough, right? To get the direction, we would have to know which way the solenoid is making a field. Is the solenoid making a field this way, or is it making a field this way? Well, that depends. Is this side of the wire in front, or is this side of the wire in front? It just depends on how you interpret the coil. If this were a real problem, I would probably do something, and I'd say, this is in front. And then you'd have to think about a slinky, and then, it'd be a nightmare. So we probably wouldn't do that. Probably just ask for the magnitude. Okay. All right. Wow. We made it through just a few slides, but this is all. It's good to get this down fundamentally. Okay, so let's take a break, and then we'll talk a little bit about eddy currents. All right, let's get going. I've lost track of time. I think I'm robbing you of a minute, but we have so much to cover. Also, I didn't answer all the questions last time. Sorry. My phone was off to the side. I didn't have the sound on. Can you explain how you got the picture next to Faraday's law? This was looking, I think you mean this, it was looking down. I was looking down on the thing turning rather than the GoPro view. That's what that was. All right, next question was, what is K? People were asking, what is K? K was, we're saying the current increases linear in that problem. So it's just a constant. It would be in coulombs per second. Just a made-up constant to give you a linear relationship. What does it say under KT? That says IS. I'm reminding you that that's the solenoidal current, IS. So I just plugged it in right away. What is theta of the angle between the flux and the flux wheel? Theta was between the B vector and the A vector whenever we're calculating flux, because it's B dot A. So you just got to think about which way is B pointing and which way is A pointing. Oh, no, I'm going to keep that here. And then this I'll keep here, and I'll turn the sound on. And I'm turning into my grandfather if he'd been alive when fanny packs existed here. Okay, the next item up for bids is about the fact that induced currents feel forces. So in that generator problem, I showed you with quite a bit of drama that, how convenient, that you have to push harder when it's drawing a current. Can we explain why we use the solenoid race again? I can't. I already erased it all. I'll come to office hours because we got to keep going. Induced currents. I can't redraw it all. I can't explain it without redrawing it. Induced currents feel forces. Okay. And then another thing, I'll explain this in a second. The force on the loop always damps it. Damps. Always damps. Okay? So I don't want you to get the idea that somehow, because we use sort of ILB to justify Faraday's law, that current is not subject to Faraday's law. It is. Because Faraday's law just says there will be a current due to induction. And if that current's in a magnetic field, it'll feel a force. So let me show you what that means. Let's go back to our old example here. Oh, yes. The square loop exiting the magnetic field. And if you didn't catch this last time, here B is B naught, and here B is 0. That's kind of what that dotted line means. It's the region where the uniform loop stops. Okay? And we had this case we were thinking about where we have the square loop, and we said it's moving out of the field with velocity v. We didn't say why or how. I mean, it just is. Some magic hand is moving it with velocity v. And we thought about the direction and everything. Let me run through that again just to make us feel better about it. We'll practice. So let's look again. This is the old square loop exiting uniform field. The first thing we did. Okay. So let's get the direction of the current. Current direction. Well, we could get it from Lenz's law. It would be the quick way. Let's practice a little Lenz's law. The loop has flux into the board, right? If we define A as in, whatever, the magnetic field is into the board. It is exiting the magnetic field. Therefore, the amount of field into the board is decreasing. And Lenz's law says current will flow to oppose that change. Okay? So let's talk our way through it real quick. I think we can do it in a small enough number of words it's worth writing on the board. So the B into board is decreasing. Okay, that's a loose sentence because the B field is constant. What we mean is the B into the board in the loop is decreasing because the loop is moving out. Because loop moving out. Okay, this is getting too long. Moving out. So current increases B. B in. There's sort of some Tarzan language for that. So the B into the board is decreasing because the loop's moving away. So induction will try to get it back. It'll oppose the change. So which way can current flow in the loop to make a B field into the board? B field is straight into the board. Your fingers are the current. There you go. It's going to be this way. Okay. So we know for sure the current's going to flow that way without doing any calculations. We have the right-hand rule and Lenz's law. Okay. What is the magnitude of the EMF? Let's see. So we're not going to solve that again. It's the first thing we did. It's BLV. Whenever you have something square or rectangular exiting a field like this, BLV. B because it depends on the magnetic field magnitude, and the LV is the change in the area, basically. So where this is L, it's a square. There you go. BLV. Cool. What was I going to say? So what is the current then? The current induced, I, we've done this a few times now. It's just BLV over R. You'd be given the resistance of the loop, R. Okay. So we got an EMF, we got a current. I forgot what we're asking. Oh yeah, we're trying to figure out the force. Okay, so now we know. Now we know that current is flowing through all four sides. So what are the forces? F1, F2, F3, F4. So the force on the loop is F1 plus F2 plus F3 plus F4. Put U. Okay. F1 through 2, 5. Okay. So let's say, what is the force on 1? Well, it's actually hard to get because it depends. It's changing in time, isn't it? Let's think. It's IL. So L is that way, like the vector IL cross B. L is the direction. And if you cross that with a B, it's going to be some force up. F. Ooh, that tickled. Up. I mean up. Sorry. We turn that down. Why we use the solenoid? Can you explain why I is clockwise and not counterclockwise? Put that back in there. Because it's got to. It's because of this. Because of Lenz's law says that the current will flow to oppose the change in the B flux, right? The B flux is in and it's decreasing. So the current says, no, let's make it increase. How do I make the B flux in increase? I create a field in. How do I create a field in? Current flows this way. Okay? You can do it with math. If you want to do it with math and define an area vector, you can. I'm just saying the Lenz's law is a quick way. So, just practice it. Read about it, think about it, work on it. I was just saying that there's a force up, right? Force up, but it varies in time. So let's just call it F, T, and it's up. Something varies in time. I don't want to calculate it. Too hard. And you'll see why. I'm not going to calculate it in a minute. I bet you a lot of you already know, right? Ft up. Okay, what is F of 2? What is the force on side 2? 0, because there's no magnetic field. Oh, yeah. Tricky, yes. That's not in the field. So you have to have a force, I, L cross B, you have to have a B. There's no B. Force on 3, here we go. Like this, and L cross B. Oh, it's going to be some force down. All right, but I don't like it because it's going to vary in time. I don't want to calculate that one. Let's say that one also varies in time, and it's down. Also here. Oh, wait, they're the same. They're going to cancel, right? That's why in this problem you don't actually have to deal with those two, is they cancel. Because you can convince yourself they're the same magnitude, right? It's the same amount of wire in the field, blah, 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 blah. Just ignore it. Those two cancel. Well, there's going to be a force. We're counting on side 4. Do you see the drama I'm building into this? Okay, it's like, oh, we almost had one, and then it canceled. Oh, here come the TIE fighters. Wait, here's Han Solo. Here he goes. Is there going to be a force on 4? Speaking of my grandfather. L cross B, yes. Oh, saves the day. 4 has a value, ILB, right? Did I want to get the actual value? Yeah, why not? ILB sine of 0, right? Because it's a sine theta, but here they're perpendicular. The wire's clearly going up, B goes in. So we would say, what is I? These are all zeros, so this is just the answer. B LV over R is I times L times B. All right. So then the famous number you would get, famous in certain circles, B squared L squared V over R. That was a joke, by the way. And it's to the left. Certain circle. Okay. So there's a net force to the left. So as you pull this loop of wire out, it doesn't just fly out. You have to pull it out. So it takes a constant force to move it at a constant velocity. Shouldn't it be sine 90? Yes, it should be sine 90. You're so smart. They are at 90 degrees, and I wanted that factor to be 1, so yes, of course. You just can't see my 9. Let me make it bigger. You see that little speck? That was my 9. Let me blow it up for you. There. God. Okay. Thank you for catching that. Okay, yeah, so the idea is this doesn't just fly out. You don't just give it something and it moves with its own momentum. It's actually damped, right? The force always damps. It's always a damping force. So I have to actually pull, and then I have to apply a force that matches the velocity that I want. So the faster I pull it out, the harder I have to pull. Okay? So don't think that that the induced currents don't feel a force because it was the force that made the induced current. No, the induced current just happens because of Faraday's law, and the ILB forces still apply. Okay? Okay. Let's see. So that is there, and we did all that. Everybody's cool with that. Okay. Now, the next question. There's 2 levels of crazy we could go into here. Let's just do one. Let's talk about what happens in a solid material. All right, so what if instead of a loop, what if I just had this? What if I had just a solid hunk of copper or anything? It doesn't have to be copper. Right, solid. Are we going to get eddy current? Are we going to get swirling currents? Is this going to happen in a solid? I mean, does Faraday know if it's a loop or it's a solid? I could say, well, let's just think about this part of it. Instead of thinking about the whole thing, let's just think of the outer rim. Outer rim's a solid. That's a loop, right? And I could also just say, let's just think about this little piece here. Oh, well, that's a loop. So it seems like there's no reason current wouldn't flow. I mean, along those paths, it's like it's a loop. Does it care if there's a loop right next to it? Can you explain why we use the solenoid radius? Oh, God. Somebody's asking why it's sine 90. It's because the sine is L cross B. L is this way and B is that way. Let's see. What's the direction of the velocity in the previous example for F4? It's that way. Colored chalk is so showy. I don't like to use colored chalk. It's also full of wax. What is the current direction of the loop is moving? It went around like that. Whew. Man, see, there's the current. It's going that way. I think you guys are just trying to help me out here. How do you find the L vector direction? The L vector is along the current. So we defined L as the length of the wire it's going through along the direction. Okay, back to this. So will current flow? Yes. So current flows? Yes. 2 S's. It's called an eddy current. All right. Now, we aren't going to calculate it. It's very difficult to calculate because it's very complicated. But it's the exact same thing. A current swirls around. Eddy current swirls through solid. How we use this technologically, and it causes a damping force. So this is a way you can resist motion. Causes a damping force. So it's used, again, brakes. You know, if you want to have brake, you can just dissipate things, and it generates heat. Okay, so now, before we were just messing around, and I did the fun stuff. Now I need somebody who wants a chance to break my nose. Oh, it could happen. If we have a power outage at just the right time, I will break my nose. This power supply is pretty old. I can't do this by myself. Someone really has to come and maybe break my nose. It's all I got, my pretty face, so I'm ready. Come break my nose, someone. All you're going to do is you're going to hold it like this and let it go. Ow! Okay? You're going to let it go, but I'm going to put a magnetic field in here, and eddy currents are going to flow. Now, are eddy currents going to speed it up into my face, or are they going to stop it? Which are they going to? They're going to stop it, I hope. So somebody come do it. I can't do this one by myself. Somebody has to come try to break my nose. What did you mean by damps in force on loop? Always damps. It means it slows it down. 125 prereq. Somebody come hold this. I won't sue you. I mean, I'm old. It doesn't matter anymore. All my lectures are already online. Doesn't matter what I look like. Yay, Shams is going to break my nose. Payback for the Hansen line. Okay, here we go. Let me see it. I always hand it to him first because I kind of go, okay, here you go. Now, let's break my nose. Ready? Well, I'm going to do 3, 2, 1, and you're just going to let it go. You ready? 3, like hold it a little higher. I want a real break. Oh, no, not that high. Okay, here we go. All right, 3, 2, 1. Do it, just do it. Okay, good, he did it. Whew. Every year I worry if the switch messes up or anything goes wrong, you never know. But yeah, you can see, if I have the switch open, it just goes, close the switch, boom. Right? That's the damping force. If you want to feel it later, you can feel it. It's pretty big. So they use it in brakes and stuff like that. There's another famous example of the damping force is dropping the magnet through the copper tube. So I want you to know it's not just moving a plate. So if I take this thing here, this is a copper tube here, and you can drop stuff through the copper tube all day and see how fast it drops. Here's a pen through the tube, chalk. If anybody wants to throw me something, I'll drop it through the tube. Does anybody have something they want dropped through the tube? I don't have any earrings on. If you take just a metal ball and drop it through the tube, it's just a metal ball, I swear. Nothing fishy. Oh, it's empty. No, wait, which one is the magnet? Let's see. Okay. If you just drop this steel ball through the tube, no, that's the magnet. Wait a minute. It's like the Baker Beerback team. Come on. Oh, man. Oh. Maybe it got stuck. I think it got stuck this year. Ouch. Oh, no, I forgot that it gets attracted to the pole. That's right. You got to get it far from the pole.
Are we even having class at this point? I don't know. It takes a long time. It's not quite that long. Oh, it got stuck to that. I forgot you have to use a plastic thing to catch it. Yeah, I forgot. See, what happened is it's moving down, so it's generating eddy currents, and then the eddy currents are pushing back on the ball, so it gets damp. But if it gets near this, it stops against the side. Oh, yeah. But if we do it like this, it's about 11 seconds. Here we go. I can hear it. I can hear it. It's coming down. And there we go. So if you want later, you should watch it on your way out, because it's pretty amazing to watch it just kind of barely go down the thing. Okay, so eddy currents are real. We're not just making this up. And next year, I'll remember to use a plastic holder. Okay. Now I'm going to explain all of MRI in 10 minutes. Shit. Why don't I just answer questions for a few minutes? I don't want to let us leave 12 minutes early, but I don't really want to start MRI. Let me give you the intro. Let's just remind you this, because I'm picking things that are useful for like the exam and helping you remember stuff. So I guess I can tee up MRI. There we go. Let's see. So let's see. I decided to put MRI back here with the magnetic fields and not in the advanced or in the modern physics part, because really you don't need modern physics to understand MRI. Let's just jump to MRI. Here we go. It only takes like probably 5 minutes, actually. It's not that long. Let's look at it. We're not even doing MRI. We're doing nuclear magnetic resonance. Speaking of crazy medical things, another use of eddy currents is Transcranial magnetic stimulation. Have you all heard of this? Where they take the two paddles and they create a magnetic field in your brain and they use it to treat disorders. And I mean, it's legitimate, I think. All the people I saw, it looked fairly legitimate, although I kept seeing the title consultant right next to doctor, which made me nervous. Right? But they say that the field is pushing the currents going around your neurons in your brain. That sort of stimulates the neurons. But I don't know that it's not just joule heating, right? I mean, it's not just the current right on your neuron. It's every charge that's free in your brain is suddenly moving around and generating heat. So I'm pretty sure transcranial magnetic stimulation is really just like a blowtorch in your brain, just very like focused and going through the cranium. So read up on it before you get any transcranial magnetic stimulation. Okay, NMR though, much more legit. Okay, so let's draw this. Here we go. Here, that's an atom, right? There is the nucleus. The size of the nucleus has been exaggerated so that you can see it. And if you look at a nucleus up close, it's got nucleons, okay? Just protons and neutrons. And a general rule is a nucleus, or nuclei, with an odd number of nucleons, which are particles in the nucleus, has a magic thing called mu. Do you remember what mu is? It has a magnetic moment. Okay? So a lot of the fundamental particles have magnetic moments. When they come together to make things like nuclei and atoms, you got to figure out what's the total effect. Is the net effect to have a total magnetic moment, or do they cancel? So here's sort of a rule we'll start with, is that if you have an odd number of nucleons, you get a mu. So remember, that was the magnetic moment. That means it'll respond to magnetic fields. It means it's creating a little magnetic field. And if you want, you can think of it as a little current loop. Right? In the macroscopic world, magnetic effects and magnetic moments are always current loops. In the microscopic world, the particles just have an inherent magnetic moment. But if it helps you, if you want, you can say, oh, there's a little wire going around the nucleus with current flowing through it. There isn't, but that's the idea. So it's just like as though that were happening. Okay? So what this lets us do is think about aligning that mu with a magnetic field. So see if you remember this. So the potential energy, and this is important for the exam, potential energy of that moment in a magnetic field B. Remember how that worked? Let's draw it real quick. And B to the right, and mu, I'm going to trick you up and put the order different than usual. Here's some mu's, and here are some mu's, All right? So let's think, if this is the B field pointing to the right, let's remember our potential energy. We called it U, big U, in that magnetic field. What was it? So one of these is the highest, one is the lowest, and one's in the middle. So just review in your mind a minute. Which one was the high potential energy? The high energy is when it is perpendicular, right? So this is high, large, high U. And this is potential energy. That's not a mu. And this is low U. Right? And I'm saying high and low and not positive, negative, because remember, potential energy, you don't really know where 0 is. I could call this 0 and say this is the positive number. Or I could call this 0 and say this is positive, this is negative. Or, if I felt wild, I could call this 0 and say this is negative and this is even more negative. Okay? But the point is we just think about changes in energy usually when we think about potential energy. And remember, the formula then that we're hearkening back to here is that U was minus the dot product of mu and B. Right, so that's a big number when they're aligned, but the negative sign is the reason that the aligned one is the low of potential energy. And when they're perpendicular, it's in the middle, and when they're anti-aligned, 180 degrees, negatives cancel. That's why this is the high. Okay, so get that in your head. If it didn't stick before, it can stick now. Thank you. So now we're going to say, what happens then if I put an atom in a magnetic field? Is it really just the normal class length? It seems longer to me. Does it seem longer today? Maybe it's because it's hot in here. I don't know. I'm dying. Let's see. So let's put an atom here in a field. Woo! There's an atom. So now we're going to put it in a magnetic field like that. All right? Or we're just going to have the atom not in a magnetic field. Magnetic field 0. Right? So this is the answer. Yes, this seems very long. I asked for it. What's the middle potential energy? It's halfway between. So if you're doing numbers, it would be 0. My point is it's all relative. So it's just between. I'll put, if we're just doing these relative numbers, it's between high and low. Is that the same equation as torque but with a negative sign? Excellent question. No. Negative sign and torque is the cross product. Ooh, wait, they have the same formula, but one is dot and one is cross? You mean dot and cross are different? Yes. Right. But they do actually have the same formula looking, and they have the same units, right? Energy is Newton meter, and torque is also Newton meter. Whoa, sometimes people get obsessed with the idea that it must mean something, that they have the same unit. It doesn't. Do the nose demo again. Oh, screw off. Do the nose demo again. Okay, so what we're going to do now is we're going to do sort of like an energy plot. You'll see these as you go into chemistry. Sometimes they're called like Jablonski diagrams if they're about electron energies or states or whatever. We'll just do this is a very simple one because this is physics, right? So we don't have to complicate things. We're not insecure intellectually. We can draw it simple. And let's draw the energy levels of this nucleus when we have B equals 0. Well, if there's no field, you could call that, I guess, 0 if you want. I mean, this is U. Let's just say it's here, right? So the B equals 0 nucleus is sitting there at that energy, right? Now, what if we apply a field? What does it do? Well, it's going to be in one of these two states. It's either going to be aligned or not aligned or somewhere in between. So then, if B, you applied some B naught, well, classically, you would say, well, it must be in this band, right? Different alignments looks like that. They can have all these energies, right? Where this would be, higher energy would be where if B is this way, mu is that way, and the lower energy would be, if B is up, mu is alongside it. And this would be if mu is that way. Right? So just all these values could happen. Right? But quantum mechanics says no. No, it's either going to be one way or the other way. Right? If it's a two-state system, then you say, no, you don't really do that. Let's just make it like this. I mean, there's things we can do to turn it and get it in between or something, but let's just say it's one or the other. Okay? So it's still true. Those are two different alignments, but we're not going to allow all those in between. We're going to say that the nucleus can be in one state or the other. So we have a two-state system. Okay? B equals 0, B. So what you do when you apply a magnetic field to really any material with nuclei in it, which is everything, is you polarize, in a sense, the nuclei. they jump into one of two states, either the high energy state or the low energy state. Okay, so you apply the magnetic field, different alignments, and you get and what really happens though is nuclei jump between the states. I'm giving you a very loose approximation between the states. Right? You might have a bunch sitting here. Maybe you've got like 20 here, and you got 3 here. And every now and then, one will jump up there, and you'll have 19 here and 4 there. Then maybe 2 will jump down. You'll have 21 here and 2 here. They're just jumping up and down. Now, when they jump up and down, they have to conserve energy. So one thing you got to think about is where does the energy go when they jump up and down? And the answer is it goes to radiation. Okay, so nuclei jump between states, and they emit or absorb radiation. All right. So I think what we can do, all we'll do is we'll get halfway through this. Let's calculate what's the frequency of that radiation. That's all we got to do, just with a couple of real numbers. Let's just get a rough estimate of where that radiation is, and then we'll be done. All right. Because we did optics already, right? So let's look at hydrogen and water. Hydrogen nucleus. Oh, no, that's the experiment I'm trying to do. Let's just look at hydrogen. Hydrogen nucleus, right? What is the mu, h? The magnetic moment of a hydrogen nucleus, which is just a proton, right? There's only one nucleon there, is 14 times 10 to the minus 27 joule per Tesla. As you would expect in MKS units, it is very small. We're talking about a single proton here, okay? And that is actually equivalent to amps meters squared. So if you wanted to think of this proton as a sort of 1 meter squared loop of current, this is how small the current would be, like pretty small. Okay, so let's put that in a 1 Tesla magnetic field. And then what we're going to do is just see what delta U is. Okay, so delta U, it's going to be 2 times mu h times t. And the reason it's 2, right, is because the difference between these two states, this is at plus mu b, and this is at minus ub. So plus ub minus ub is 2. Right? There's got to be a 2 in there to get the energy difference between them. So we say those things, well, this is mu and this b, not t is the unit. Right? 2 mu b. Right, so we say, okay, that's 2 times 14 times 10 to the minus 27. Right, and B is 1 Tesla. And you get some ridiculously small number, 4.2. You just get a number that I didn't write down. Okay. So then you say that's the energy. Well, I could probably do it. I think it's 28 times 10 to the minus 27. I'm not sure. Okay. But now we got to figure out, what did I mean? How do we figure out the radiation property? This is equal to the energy of the photon that it makes. Okay? We talked about light as a wave, and it is a wave, but it can also act like a particle, and the particle can have a certain energy. All right? That's part of the modern physics stuff, is that light acts a little bit like a wave and a little bit like a particle. And the energy of a photon is h, a number called h, times the frequency of the photon, and we use nu in this kind of world. Right? And h is the famous Planck's constant, 6.26 times 10 to the minus 34, and I forgot the unit, and I didn't write it down. Meters squared kilogram per second if we want to do it MKS. All right. So you can see what's going to happen is we're basically just going to say 2 times 14 times 10 to the minus 27 divided by, that looks small, but look how small this is, 10 to the minus 34. And we're going to get a frequency that is 4.2 times 10 to the 7 hertz. So that's your rough estimate that where is the radiation that occurs when the nuclei jump back and forth in a 1 Tesla field. It's in the megahertz region, okay, roughly megahertz. This is why NMR uses megahertz radiation. Right? So we'll finish it Tuesday. We'll talk a little bit more about what you really do in the experiment and how you turn it into an imaging modality, because it's interesting.